So this video is for quiz 15 and you've got the start of SC25, which is what we're doing at the moment, the test for ions, as well as revision from the first term, CC13 to CC15. Even though it's a new topic, I think the mark scheme will clear up any issues you might have with the questions from SC25. It's all effectively just tests and colour changes that you have to learn. What I would say is pay close attention to the mark scheme on questions around flame tests. Be clear on why we don't use a wooden splint, why we use a wire instead, and be clear on why you're dipping it into water, or you'll see on the mark scheme they say you can dip it into hydrochloric acid instead. It helps the solids to vaporize. So just be clear on those little practical details which you'll pick up from the mark schemes. But other than that, you are essentially, you're learning your color changes. What I'm going to go to instead is question 24, which is a 6 marker back on the rates of reactions topic. You've definitely seen this before. I think it was in one of your previous booklets, but it wasn't particularly well answered. So I'm just going to quickly run through how to structure your answer for a question like this. So you're asked to use the results to explain in terms of the behavior of particles, the effect of changing temperature and the effect of changing concentration on the rate. So there's two parts. You need to talk about concentration and you need to talk about temperature. So I'm going to split my answer into 2 paragraphs. The first one, I'm going to talk about concentration. And when I want to talk about concentration using these results, I'm going to specifically talk about experiment 2 versus experiment 3. And the reason I'm doing that is you can see that there's an increase in concentration as you go from 2 to 3, but the temperature remains exactly the same. Therefore, this change in the time is entirely due to concentration. So what I can say is that when I use 40 grams per decimeters cubed, I get a faster rate of reaction than when I use 10 grams per decimeters cubed. And I know this because the cross disappears in 20 seconds instead of disappearing in 80 seconds. Temperature remains constant. Okay, so that's all you would need to state from the table. But I would only refer to experiment 2 and experiment 3 when talking about concentration because temperature stays constant. Once you've explained that rate has increased with an increased concentration, you need to say why in terms of particles. That's straight from your carousel. You're just going to say if there's more particles per unit volume, you get increased frequency of collisions. The next part, you're going to talk about temperature, and when we're talking about temperature, okay, we're going to be talking about experiments 1 and experiment 2, because you can see here, looking at this data, that the concentration stays the same, but the temperature increases. So this change in the rate is entirely due to temperature. So again, I can say that by increasing the temperature from 20 degrees to 40 degrees, the rate of reaction increases. The cross now disappears in 80 seconds instead of 320 seconds. Concentration remains constant. So that's me using the results to explain, but I need to do it in terms of the behavior of particles. So I will say rate of reaction increases at higher temperatures because particles at higher temperatures have more kinetic energy, or they move faster, therefore they collide more frequently. Always use the word frequently. The other thing you need to say for temperature is that at higher temperatures, more particles have the necessary activation energy, so there are more successful collisions. So the particle bit is straight from your carousel, but just make sure that you're structuring your answer in a way that it's clear. So I would split this into 2 paragraphs, and when you're explaining or referring to the data, just refer to 2 experiments each time. The next one is from CC15, which we were quite good at. The only thing that this might cause problems, the only reason this might cause problems is actually drawing the molecules. So CH4 we've seen many times now, it's methane. Carbon is in group 4, it can form 4 bonds. Hydrogen only forms 1, therefore I'm definitely going to be putting carbon in the middle, and I'm going to be putting the 4 hydrogens around it. So carbon gets to form 4 bonds, hydrogen can only form 1. Cl2, again we've seen many a time, it's just got a single bond in between. I know this because chlorine's in group 7, therefore it only wants to form 1 bond, so I'm not going to have a double bond between those 2 chlorines. CH3Cl, again, you might not know which one to put in the middle. Carbon can form 4 bonds, alright, so I would definitely put carbon in the middle. Hydrogen only forms 1 bond, so that means you're putting 3 hydrogens around it. And then chlorine as well only forms one bond, so you're going to put chlorine coming off carbon. I think when I gave this to you before, some of you were putting the chlorine coming off one of the carbons, sorry, one off the hydrogens. If you do that, if you put the chlorine there, you've got hydrogen forming 2 bonds, which it can't do, and you've got carbon only forming 3. So just make sure at the end that carbon has 4 bonds, hydrogen has 1, and chlorine has 1. And then at the end, HCl is just going to look like this, hydrogen forming 1 bond, chlorine forming 1. Now you can use this table to help you. You can see that there's no chlorine-chlorine double bonds, which tells me it's definitely a single bond between these two. You can also see that there's, oh, there is a hydrogen-chlorine bond. Yeah, okay, so that's, I think, the mistake that was made last time was people were doing that, and you do have a hydrogen-chlorine bond, but that's because you've got HCl. All right, that's not how we're going to draw it. Carbon needs 4 bonds, hydrogen and chlorine both need 1. Once you've got them drawn, you're just using the bond energy values, calculating all the bonds you need to break, all the bonds you need to make, and then it's bonds broken minus bonds formed. This next question should be familiar to you. You saw it on your mocks as well. There is a graph that goes alongside this question that I just haven't printed, but you can use this information here to work out the rate of the reaction. You can see it's essentially halving every minute, so the answer here is 13, although there is a graph that goes with it. So that's just filling the answer in there. And then this caught a lot of you out in the mocks. It says state and explain what happens to the rate of the reaction. And I think the graph is the reason it caught a lot of you out. The graph that came with this question had volume versus time. And I think a lot of you read this as kind of as rate of reaction, as the graph itself was the rate of reaction. And you saw that this line is increasing. So you said the rate of reaction was increasing over time. And that's not true. Okay, we can see here from these values that the rate of the reaction is decreasing over time. And the reason why is because when the particles get used up, there are less particles and therefore less frequent collisions. So I think some of you just misinterpreted this graph. This is volume over time. And you start off by producing quite a high volume, and then the rate that you're producing that volume of gas slows down. But obviously you end up with a greater volume of products at the end than you started with, but the speed at which those products are being produced slows down over time. So the rate slows down over time. The reason, because the particles are being used up, you get less frequent collisions. This is from CC13 on groups, so it's one of those redox reactions. State what you see. So many times you guys just tell me bubbles. Okay, you're not making a gas here, you are not seeing bubbles. With these displacement reactions, it's always a color change. The halogen by itself is responsible for the color. And actually chlorine dissolved in water, because these are always carried out in aqueous, is colorless. And then the halogen over here by itself is iodine, and iodine dissolved in water looks brown. So it's going to go from colorless to brown. You have to tell me the color change, not just say color change. The color should always get darker. So if you're in any way confused about which way around it goes, make sure it starts light and gets darker. Write the ionic equation. All right, when you're writing an ionic equation, you need to identify what's covalent and what's ionic. So my halogens are covalent, they don't contain any metals. These two are ionic. If it's covalent, it stays exactly the same, so Cl2 stays as Cl2. If it's ionic, you need to split it into ions. So potassium iodide splits up into Ki. By that I mean just stick a plus between the K and the I. But because you have to show that they're ions, you need to put the charges. Potassium's in group 1 with a +1 charge, iodine's in group 7 with a -1 charge. There is a big 2 in front, and that 2 refers to the K and it refers to the I. On the other side, you're going to do the same thing. You're going to have 2K plus, you're going to have 2Cl minus. And then again, my last thing here, iodine is covalent. If it's covalent, it doesn't split into ions, it stays the same. You cancel out the spectator ions. They are the ions that are the same on both sides. And this is your ionic equation, and you're getting 3 marks for that. This bit should be okay, explaining why chlorine is more reactive. You're just talking about the fact that it's smaller and you've got a greater attraction between the nucleus and the outer electron, so it's easier to gain an electron. Explain why this is an example of redox. So redox is the words reduction and oxidation kind of smashed together. So you need to show that something's being reduced and something is being oxidized. I think the easiest way to do this is through half equations. So what I will do is I'll take my ionic equation and I'll write one of them for chlorine. So when I'm doing this, I just write down the Cl2 from the left hand side. All right, then I go to the right hand side of this equation and I find chlorine again, and on the right hand side it's present as 2Cl minus. And then I'm going to do the same thing for iodine. I find iodine on the left and it's present as 2I minus. and on the right hand side iodine is present as I2. And now I need to decide in terms of electrons if they're losing or gaining. So chlorine starts off neutral, it ends up negative. If it's ending up negative, it must be gaining electrons. There are 2 chlorines, each of them gain 1, so you must be gaining 2 electrons. On the other one, you've got something that starts off negative and ends up neutral. It's negative because it had gained electrons. If you remove those electrons, it will be back to being neutral. Chlorine is gaining electrons, so I would write reduction is gain of electrons, and then under here I'd write down oxidation is loss of electrons. So Ulrich, oxidation is loss, reduction is gain, but you need to tell me what's being lost and gained. You have to mention the word electrons there. If you wanted to write this in words, you can say chlorine is being reduced because chlorine is gaining electrons. That's fine, you can call this chlorine. You cannot call this iodine, you have to call this an iodide ion. If you refer to this as iodine and say iodine is losing electrons, iodine is being oxidized, then you're wrong. You would have to say the iodide ion is losing an electron, the iodide ion is being oxidized. To avoid that, I would just write the half equations. It didn't specify you needed half equations here, but sometimes it does. So it's in your best interest to be able to write these. Sometimes they are required, and it avoids you making that mistake with language. The last question here is just another rates of reaction question. You may hopefully remember that when you've got graphs, you can work out the rate of reaction using a graph. And if you're asked to work out the rate of reaction at a specific time, so here at 40 seconds exactly, what is the rate of this reaction? You come up here to line A and you draw a tangent at exactly 40 seconds. Now they've drawn that tangent for you. Once the tangent is drawn, you need to get the gradient of the tangent. So to do that, I'm going to pick 2 points on the tangent. Ideally you want to pick them as far apart as possible, and ideally you want them easy to read. So I picked the 2 points on opposite ends of the line because A, they're far apart, and B, they're really easy to read. So this point right here is at 72, so I can read that on the x-axis, and on the y-axis it's at 90. And this point down here on the x-axis is 0, and on the y it's 30. So they're really easy points to read. They're not in between a square. Once I know that, it's just change in y over change in x. So my y values, that's my y value, that's my y value. The difference between 90 and 30 is going to be 60 over the change in x. 72 and 0, the difference is 72, so you end up with 60 over 72. Divide that, 0.83 is your answer, so I should have written that there, but that is the rate of reaction.